Or I'm going to keep it slightly more generic for what we do after this. N times the expected energy or the average energy for one particle. All right, let's see if we can make some sense of it, put some pieces together here. I know that my energy is equal to N times this value of the average energy for one particle, this is the total average energy. If I want to look at how this changes with respect to frequency, then the E dF is going to equal, well, that value for 1 times dN dF, which we solved. So that is the value for E times, divide by dF, and you got 4 pi L cubed over C cubed F squared. So 4 pi L cubed over C cubed F squared. There's going to be a couple of hand waves in this, and then one of those hand waves is coming up real soon here. Light has two modes of polarization, and in all the textbooks I see, they usually say N. Light has two polarizations, and so therefore you throw an extra 2 in there. So I'm just going to throw that extra 2 in there for polarization of light. And so we now end up with L cubed. The EDF is equal to this value of energy, 4 of 8, because I threw the extra 2 in there, pi L cubed over C cubed F squared. Multiplying both sides by dF, I have dE is equal to, again, that kdt, 8 pi L cubed over C cubed F squared dF. It's now trying to get into the right form. dE is the energy. It's a differential of the energy for on this shell, in the shell. If I want the energy density, well, with any density, you divide by some sort of space. So I'm going to divide by L cubed, which is the volume of my cavity. And so I end up with the differential of my energy density is equal to the value of the average value for one particle or one wave times 8 pi F squared C cubed dF. This was a prediction made by Rayleigh and Jeans. This is the two different people. Ward Rayleigh and John Jeans. I'm assuming it's pronounced Jeans as opposed to Jeans or something like that. They're both British. So if we look at that, if I want to figure out what is the energy density over an entire spectrum, well, we can just integrate. So I need to erase some of this stuff. Any questions before I erase? That, don't need that anymore, we'll keep that. All right. So the total energy density, I had du is equal to, I'll just go ahead and stick the kVt in there. kVt times 8 pi over c cubed f squared df. Now I'm going to integrate from 0 to infinity. I get u on this side. Over there, I got this constant up front, kVt 8 pi over c cubed, and then from 0 to infinity on the frequencies, integral of f squared df.
F cubed over 3.
So I get a 3 over here, I get an f cubed from 0 to infinity. Therefore, what is the energy density over the entire spectrum?
Infinity?
Yes. Now, considering that we're all still here, we have not died from extreme radiation poisoning, that's not right. If you look at this prediction here in the differential form, so in essence the slope, if you look at that, it does match it somewhat. It works very well in the low frequencies. Remember, frequency and wavelength are inversely proportional, so that's why it agrees on both sides of the hump. It works very well for those values, but it really, really does not work well for high frequencies. If it did work for high frequency, so we start getting into higher frequency, the ultraviolet and so forth, that would mean that we have this extreme amount of radiation. And this is known as, coined by Paul Ehrenfast, as ultraviolet catastrophe. So the question is, why is it off? Where is the issue with what their approximations were? Some of you might have guessed. It has something to do with this piece right here that I kind of isolated. All right, questions before we bring in Planck and quantum. All right, so they're trying to figure this out. So what Planck does is he looks at the curve, looks at the data, and he comes out with an equation that works. He has no idea why the equation works. He just comes up with an equation that will fit that curve. And the equation that he comes up with is there we go. du equals, there's so many different forms of it. I will take this one over here. At some frequency f, 8 pi hf cubed over c cubed, 1 over e to the hf over kVt minus 1 df. This is what Planck comes up with. And then he spends the next couple of years trying to rationalize it. There's a whole bunch of quantum physics where there just seem to be a whole bunch of guesses that turn out to be right. But that's probably true for any theorist. You throw it against the wall, most of it's going to fall off, some of it sticks.
So he doesn't know how he got that equation?
He couldn't rationalize why that equation works, other than it fits the data. But Patrick, looks like you're struggling to read.
What's the power of the E?
This right here? Oh, yeah. That is hf over k b subscript b times t. F is frequency. H is now known as Planck's constant or Planck's constant. That's how much you want to anglicize it. Capital T is temperature, and K sub B is Boltzmann's constant. So let me get some values for you. Got a bit of it there. So H is 6.626 times 10 to the negative 34th joule seconds. K sub B, not to be confused with the wave number, is 1.38065 times 10 to the negative 23rd joules per Kelvin. So, how do you get there? What did he ultimately decide? If you take a group of atoms and you heat them up, you should get a distribution of energies in it. There'll be some with a very high energy and some with a very low energy, and you basically get a relationship of distribution along the order of E to the negative E sub n, so energy at some particular level, over kBT. This is known as the Boltzmann distribution. I'm not going to justify that for the sake of time, and my notes are scattered all over the place to justify it. So if I want to figure out the probability of a particle being at a particular energy level, I basically figure out the probability of anything being at that energy level divided by the probability of all the energy levels. In essence, the probability of being at some energy level n is going to be e to the negative e to the n over kBT divided by the total, n equals 0 to infinity. I guess I shouldn't use n twice. We'll make it I. E to the negative E subscript I over kBT. So this is the probability of being at a, so this is the, I guess, unnormalized distribution of being at a particular energy level divided by all of the possible energy levels. So the expected energy then for a particular item should be, well, whatever the energy at that level is, times the probability of being at that level. Well, since the particle could be at various levels, actually, it's the sum. N equals 0 to infinity. Do I want to start at 0? Yeah, I did. So to find the average value of the energy for a particle is you would basically look at each energy level times the probability of that particle being in that energy level. Let's do a little math here. So I have the energy, so I'm adding up n equals 0 to infinity of whatever the energy is at level times the probability of being at that level divided by I equals 0 to infinity of, not that, e to the negative, oh, that's combining two different equations here, which is the sum from n equals 0 to infinity of e to the n, and then we have e to the negative e to the n over kVt, divided by the sum, I equals 0 to infinity of e to the negative. So just the energy times the probability. Oh, that's e sub I there. So the denominator here is going to be common. So if this is just a sum, an infinite sum here, but I have a common denominator which I can just factor out. And so this becomes the sum on top of e to the n, capital E to the n, and then Euler's e to the negative e sub n over kVt over our common denominator. I guess I could use any letter at this point, but e to the negative e to the I over kVt. I feel like I lost an n in there. Oh, yeah, okay. Now, so none of this is particularly earth-shattering as long as you understand the Boltzmann distribution. Here's the thing that Planck did. He said, assume that the energy is a multiple of HF, where n is positive integers. Now, it might seem like strange of, I don't know how he played around with it. I haven't read the history to figure out the struggles that he went through, and they may or may not exist that someone's documented it. But I wonder if he had the suspicion already, or whether he played around with it and eventually just had, tried everything else. Why don't I try this? Now, what we're saying here is that energy is not not every energy is possible. It's going to be some, for a particular frequency, it's going to be some multiple of this. This is Planck's constant, this is the frequency, and this is some positive energy. If you think about it, if I did the integral from 0 to infinity of 1 over x squared, I would get negative 1 over x from 0 to infinity, which would be 0 minus negative infinity. So integrating this function from over all of the values of x, I'm going to get it's infinitely large. If instead I say that not every number is possible, that if I just integrated from 1 to infinity, so let's cut out all the stuff that it can't be smaller than 1 over x squared dx. So I lost my dx there. I'm still getting this, except that my limits have changed, and I'm now going from 0 minus negative 1. So just by eliminating some possibilities, I take my area under the curve from infinity down to 1. So it's not too far-fetched to say that if we just restrict, it can't get too small. There's precedence for our having a finite value. Let's simplify this. We're here. I'm going to let x equal e to the negative hf over kBt. So my equation becomes now the sum of, well, e is nhf times x to the n divided by the summation of x to the n. This is going to be my expected value. Well, we're doing this for a particular frequency, so h and f can factor out, so we can pull out the hf, and I'm left with n x to the n over an infinite sum of x to the n. All right, let's take a look at this one first. The summation of x to the n is equal to 1 plus x squared plus x cubed plus, and so on. What does that sum equal? Pardon? Infinity. Well, not necessarily.
2,
Pardon?
2.
I was looking for an equation more.
Oh.
I think the equation I first saw in Algebra 1, so, I mean, it's an algebra thing. I know they changed what they teach in the courses since I took it, so 50 years later. All right, let's assume this is some value of s. If I multiply every term by x, I get xs. On the right-hand side, on the left-hand side, well, I multiply each of these by x, and I get x plus x squared plus x cubed plus, and so on. And now I subtract. On the right-hand side, I get s minus xs. On the left-hand side, I get 1. All the higher order x values will cancel out when I subtract. If I factor this, I get 1 is equal to s times 1 minus x. And so my sum is just 1 over 1 minus x. This would be the sequence or series, whichever one is the sum of, if x is less than 1, then we get this. Well, if we think about it, I have x is represented by this. If the frequency is 0, x is 1. If the frequency, but frequency can't be 0, then we're dealing with a non-existent wave. If the frequency is infinitely large, this whole thing goes to 0. So x is not bigger than 1, therefore each term that we're adding onto it gets smaller and smaller and smaller. So it does have